Let's start today by looking at three different vector-valued functions. F of t equals cosine pi t sine pi t, g of t equals cosine 2 pi t sine 2 pi t, and h of t equals cosine negative pi t sine of negative pi t. Now, if we go through and eliminate the parameter, we would find that all three of these equations have the same xy equation. And so that means they all trace out the same shape in the xy plane. But they trace them out very, very differently. To see this, I'm going to go and plot these curves starting at time equals 0 and going all the way up to time equals 2. So I'm going to plot these over a 2-second interval, essentially. And all I want you to do is pay attention to the motion of the point. So even though these three guys traced out the same curve, they did it in a different fashion. If we sort of hold the first curve f of t as the gold standard, it got the job done in 2 units of time, let's say 2 seconds. Then g of t was moving twice as fast because it managed to complete a full cycle every 1 second. It was always twice as far around than g was. Whereas h of t managed to get the job done in 2 seconds, but when compared to the other curves, which went counterclockwise, this one went clockwise. So it's possible to draw the same shape, but to draw it in very, very different forms, though. Now, what does this have to do with our topic today? Well, just notice something. Imagine we were to compute the derivatives at each one of these points right here at the starting point. What would the derivatives look like? Well, f prime of t would be the vector negative pi times the sine of pi t, and the second component would be pi times the cosine of pi t. So when t is equal to 0, we're going to get a vector who points straight up pi units, the vector 0 pi. Now in the second equation, when we differentiate g, we're going to get g prime of t is equal to negative 2 pi times the sine of pi, 2 pi t, and 2 pi times the cosine of 2 pi t. So when we plug in time equals 0 and get the tangent vector, we're going to get the vector 0, 2 pi. So it points in the same direction, but it's twice as long. And lastly, if we take the derivative of h, we're going to get negative pi times the sine of pi t, and negative pi times the cosine of pi t. So that if we plot time equals 0, we're going to get the vector negative, or 0, negative pi. So notice that this vector, in addition to being tangent to the circle, which is what we figured out was going to happen last time, manages to describe both the directionality of the curve. In our first 2 examples, it's describing motion in this direction, whereas in the last example, it's describing motion moving that direction. And it also gauges the relative size. The first and last curves were moving at the same speed but in opposite directions, and so their velocity vectors are exactly opposite, whereas the curve in the middle was moving twice as fast, and its derivative vector is twice as fast. And so that's going to be the theme for today. There's one additional meaning to the tangent vector. It acts like velocity. So imagine we had a vector-valued function. So we've been thinking of the graph of a vector-valued function as a curve, a plane curve or a space curve. So this curve that has some flow to it. And how we got to that thinking was, you give me a time t0, we could plug it into this function f of t0, and the result is a position vector, a vector rooted at the origin who specifies a certain point on this graph right here. What we saw yesterday was that if we took the derivative of this vector-valued function, then we got a vector who pointed in the tangent direction of this curve right here. But the previous examples have shown a little bit more than that. Not only is it parallel to this curve, or tangent to this curve, but it actually points in the direction of flow. And the bigger the arrow, the faster the curve is flowing. Well, this might sound familiar to you. In Calc 1, if we had a scalar function that represented a position at time t, f of t, then when we took the derivative of that function, we didn't just call it the derivative, we called it the velocity at time t. and it meant something to us. A velocity expressed how fast you were going and what direction you were going in. And that seems to be exactly what's happening with our derivative vectors right now. And so we're going to take the language we used in Calc 1, and we're going to apply it here in Calc 3. So f prime of t is sometimes called the velocity vector at time t, and f of t is the position vector at time t. What this means is we can give another sort of geometric meaning to the velocity vector. In particular, we can describe what its direction means and what its magnitude means. The direction of the velocity vector is indicating the flow direction. It's telling us what way the curve is moving. So if we were at a specific point on some curve, say we had a curve shaped like this, and I didn't know how it was sketched right here, but if I knew that the velocity vector at this point was pointing like this, then I would know that the curve has to be flowing at least around this point in that direction. What about the magnitude? Well, in Calc 1, when we talked about velocity, if we took its absolute value, we called that the speed. And so we'll use that same name here. So the longer the arrow, the faster something's moving right here. So the magnitude of velocity is called the speed of the particle, and its direction is the flow direction, or the tangent direction, as it's sometimes called, and what we saw last time. It turns out that these ideas are very useful when you're trying to sketch something fairly complicated. Let's plot the function g of t equals t cubed minus 3ti plus t to the fourth minus 18t squared j. Now, if we tried just to straight up plot up points, we'd get a lot of confusing information. We'd get this collection of points for times 1 through 3, which corresponds to this small sliver of graph, and that's just not enough to work with. But think about this. When we were in Calc 1, we didn't just plot points. We used the derivative to figure out when a curve had a horizontal tangent, when it had bends. Could we apply that same idea here? Well, the derivative of this function, when it's written in its component forms, is 3t squared minus 3, and then 4t cubed minus 36t. Now, when we were looking for horizontal tangent lines in Calc 1, we set y prime equal to 0. Well, if I wanted to look for a horizontal tangent vector, then that would mean I would need the y-coordinate to be equal to 0. So there's at least a nice piece of symmetry right there. So let's set that y-coordinate equal to 0. We'd get 4t cubed minus 36t equals 0. I can pull out a 4 and a t from both pieces. That'll get me 4t times t squared minus 9 equals 0. Well, 4t equals 0 gets me t equals 0. T squared minus 9 equals 0 gets me t squared equals 9, or t equals plus or minus 3. That means there's exactly 3 times on this graph when the curve is moving horizontally. At time equals 0, at time equals 3, and at time equals negative 3. Well, let's see. G prime of 0, when I plug in, will be minus 3, 0. So I know that at this point, the graph is moving horizontally to the left. At g prime of 3, we'll work this out, and we're going to get 24, 0, which means at this point, the graph is actually moving horizontally to the right. If we did g prime of negative 3, we'd also get 24, 0. And if I plot the value at time equals negative 3, I would come up with g of negative 3 is equal to negative 18, negative 81. So it'll be the mirror image of the point we've plotted right here. This gives me a little bit more information. I know I'm going to start at this point, and I'm going to be moving to the right. I somehow have to connect up to here, but at this point I'm going to be moving to the left, and so I'm going to come down and move to the right again. But that's not the only kind of interesting direction we could do. We could also talk about velocity vectors who point straight up and down when you're moving vertically. That would happen when your x-coordinate vanished. So if we set the x-coordinate equal to 0 and solve for it, we'll get that t squared is equal to 1, or t is equal to plus or minus 1. So there's 2 values when we're moving vertically. If we do g prime of 1, then we're going to find that g prime of 1 is equal to 0, comma, negative 32. So at time equals 1, which was this point right here, this graph is moving straight down. On the other hand, at g prime of negative 1, we're going to end up with 0, comma, 32. Now I didn't plot that point, but if I were to work out what g of negative 1 is, oops, forgot the prime above, we would work out that g of negative 1 is equal to 2, negative 17. So it'd be a mirror image point right here. And that's it. These are the only places where this graph can be moving vertically or horizontally. Can we put all of this information now? We know that no time earlier than t equals 3 is it ever moving horizontally or vertically. So that means the graph has to come down, pass through this point, but it has to be tangent to this line right here. So as it passes through time equals minus 3, it's got to go like this. Well, the next time we plot it is right here at t equals minus 1. Between time equals minus 3 and minus 1, it can't be going, it can only be moving to the right, and it can only be moving up because it's not allowed to change the directions. So it sort of has to come up like this. Between time equals minus 1 and time equals 0, it's got to smoothly connect these points, but it also has to be tangent to these circles. So it's got to be going horizontal by the time it hits 1. From time equals 0 to time equals 1, it's got to go from being horizontal to vertical. And then from time equals 1 all the way down here to time equals 3, it's got to go from going vertical to going horizontal. So put it together, and we get this graph here. So we find that this plane curve is something like a cursive W. Let's revisit this picture again right here. If we have a position function, and that's what we think of vector-valued curves as positions of moving particles, then the first derivative is called the velocity vector. But you might remember from calculus that we gave the second derivative a name as well. We called it the acceleration at time t. And so we're going to have an acceleration vector for curves. And just like we did with velocity, we're going to draw this acceleration vector at the point on the curve. In Calc 1, we sort of thought of acceleration as something that speds you up or slows you down. That's not exactly what it does here in Calc 3. And to do that, I'd like to give an example first. Let's revisit this guy, cosine pi t, sine pi t, from the beginning. We know that this particular function traces out a circle counterclockwise starting at 0. If we work out his velocity, f prime of t, is going to be the vector negative pi sine of pi t, or pi cosine pi of t. If we were to plot that vector at a couple of different points, this might be what some of those vectors look like right here. But here's the important part about these vectors. Let's take the magnitude of the velocity. Remember that the magnitude of the velocity is called the speed of this particle. So that's going to be the square root of the first component squared, pi squared sine of pi of t quantity squared, plus the second component squared, which is pi squared cosine of pi t quantity squared. So I can factor a pi out of both of these pieces, and what I'll be left with is the square root of pi squared times the sine of pi squared, pi of t quantity squared, plus the cosine of pi of t quantity squared. But sine squared anything plus cosine squared of that thing is always 1. That's the Pythagorean identity. And so this is just the square root of pi squared, or pi. So what that tells me is that this particular curve moves around the origin at a fixed speed. It neither speeds up nor slows down. Nevertheless, it does have an acceleration, though. If we were to go and take a second derivative, the acceleration would be, well, let's just differentiate one more time. We'll get negative pi squared times the cosine of pi t. And we'll have pi squared negative sine of pi t. And I guess if we look at that, we could pull a negative pi squared out, and we would get back the original function. We just get cosine pi t sine of pi t. So what that means is that at every point, the acceleration vector is always pointing in the opposite of the position vector. It's always pointing right back in towards the center. So what is it that acceleration measures if it's not measuring changes in speed? To make sense of this, let's go and take a look at what an acceleration vector really means. So imagine we have a time t0 and a position vector who's pointing to a specific point on the curve. At this point on the curve, we'll have a velocity vector, the vector v of t0, who is nothing more than the first derivative. And then we're also going to have this acceleration vector, and we want to try to figure out what it is that the acceleration vector is telling us. Now remember, the acceleration vector, that's just going to be the second derivative of this function, evaluated at t0. To help me make sense of this function, I'm going to introduce one new vector. This vector right here, called capital T of t. He's sometimes called the unit tangent. And so all this is it's a tangent vector parallel to the velocity vector and pointing in the same direction. With the help of this unit tangent, we'll be able to decode what it is that the acceleration vector does. So, in order to see this, well, let's remember that the acceleration vector is nothing more than the derivative of the velocity vector. But what's the velocity vector? The velocity vector is some multiple of the unit tangent. In fact, the multiple is the speed. Oops. Speed's not a vector, it's just a scalar right here. So the velocity vector is equal to the speed, how fast you're going, times the unit tangent, the direction that you're going in. Now this here is a scalar product. To differentiate it, we could use the product rule. We saw that yesterday. So we'll have the derivative of the first times the second plus the first times the derivative of the second. So what that says is, that acceleration can be written as a sum of two vectors. One of these vectors is parallel to the velocity vector, and its magnitude is the change in speed. This is the thing that we're sort of used to when we talk about acceleration. Acceleration has something which changes speed. So there's a part of the acceleration vector who does that. It's a vector, it acts in the same direction as the motion, and its component, its size, is the change in speed. But what about this second part right here? This component. What is this t prime right here? Well, this is kind of a cool and surprising result right here. I'll do a little bit of a dogleg for this result. We know that if we take t dotted with t, well, we learned this from the dot product. If you dot any vector with itself, that's simply the length of that vector squared. But since this is a unit vector, that length is 1. So what I'll do is I'll differentiate both sides of this equation. On the right-hand side, if you differentiate 1, you get 0. On the left-hand side, well, it's a product, a dot product. But the product rule still works. So it'd be the derivative of the first dotted with the second, plus the first dotted with the derivative of the second. So what we have here is t prime dot with t plus t dotted with t prime. Now the dot product doesn't matter the order in which you multiply things together, so this is just 2 of t dotted with t prime, which is equal to 0. So if I divide both sides by 2, then I get the equation t dotted with t prime is equal to 0. In other words, this vector t prime is orthogonal to t. So look at what we've just said here. We've said that the acceleration vector, the vector in orange, can be expressed as a vector who is parallel to v of a certain length, and it can be expressed as a vector who is orthogonal to v. And these two vectors together get me the acceleration vector. So now I can see the two components of acceleration. The parallel component changes speed. This component right here changes direction. Or if you'd like, it changes the curvature. this yellow vector is always at right angles to the direction you're going, and it's pointing in the direction that the function is curving in. And if you think about that in sudden hindsight right here, remember back to Calc 1? Before we talked about acceleration, we just had a second derivative, and the first thing we used the second derivative for was for concavity. If the second derivative was negative, then the graph curved down into the negative direction. If the second derivative was positive, the graph curved up. It curved into the positive direction. And so that's all we're seeing here, is that the graph curves into the direction of acceleration. So let me go back to this velocity picture and redraw it again where I can name these vectors a little bit more clearly. So imagine that you have a curve, and a point in particular. You have a velocity vector. The velocity vector is simply the derivative of position. You have an acceleration vector. The acceleration vector is the second derivative of position. There is a unit tangent vector. This unit tangent vector is nothing more than the velocity vector divided by its length. Points in the same direction, but has length 1. We've also seen that there is a vector who is orthogonal to this, and that vector is t prime over t. Now, if we were to take t prime over t and divide it by its length, what we would do is we would actually take this and shorten it down to being a unit vector. And so this unit vector, who is at right angles to the unit vector t, is called n, the normal vector. So let me put their names back on here. And we can take the acceleration and write the acceleration as a sum of two parts, a part parallel to the tangent and a part orthogonal to the tangent. Once upon a time, we called this a parallel and a perp, and these are sometimes called the parallel component of the acceleration and the orthogonal component of the acceleration. The parallel component of the acceleration is responsible for changes in speed. The orthogonal component of acceleration is responsible for the curvature, what direction a curve it wants to turn in. Given the vector valued function f of t equals t squared plus t, comma 3t minus 2, compute the velocity, the acceleration, the unit tangent, the unit normal, the tangential component of acceleration, and the orthogonal component of acceleration at time equals 1. Whew, lots of things to check right here. Well, let's go and do this in small pieces. Out of this bunch, v is the easiest to do because v is just a derivative. So v prime of t, we'll just differentiate our function. We'll get 2t plus 1, comma 3. And if we evaluate that at 1, we'll get that v, which is the velocity at 1, is 2 plus 1, comma 3. So we get the vector 3, 3. On this list, the next easiest one to compute might be the unit tangent, because all the unit tangent is it's the normalized velocity vector. So all we need to do is work out the length of the velocity vector and then divide v by that. So if I'm looking for the unit tangent at 1, all I really need to do is take the velocity vector at 1 and divide by the velocity vector at 1's length. So the velocity vector at 1 is 3, 3. The length of this vector is the square root of 9 plus 9. So let's see. That's 1 over the square root of 18, which is 3 root 2, times the velocity, times the vector 3, 3. So if I just scale this in, I notice that the 3's will cancel, and I'll get the vector 1 over root 2, comma 1 over root 2. That's my unit vector parallel to velocity. What's next on this list? A is easy to do because A is simply a second derivative. So all we'll do is we'll take our first derivative and differentiate it once more. We'll get 2, comma 0. And easy cheesy. If we plug in a equals, or t equals 1, then our acceleration vector will just be the vector 2, 0. What's next on this list? Well, we could try capital N. Remember that capital N is the unit normal, and we found it by taking the derivative of capital T and dividing by the length of capital T. That was how we found it by that formula. Now, while this formula was theoretically useful in helping me understand acceleration, it's almost impossible to use. Just look at it. We need to take the derivative of t as a function of t. Now remember, I worked out t only at one point. If I want t of t is the velocity of t divided by the length of the velocity of t. So the velocity was the function 2t plus 1 comma 3. The length of that vector is going to be the square root of 2t plus 1 squared plus 3 squared. And so that means it's going to be the vector valued function 2t plus 1 divided by the square root of 4t squared plus 4t plus 1 plus 9, comma, 3 over the square root of 4t squared plus 4t plus 1 plus 9. That's what the unit tangent looks like at every single point right here. Remember, whenever you normalize a vector, you tend to get these square roots in the denominator. So if I want to work out capital N, I get to differentiate this, then I get to work out the length of that derivative, and then I get to divide by it. No frickin' way. Instead, I'm going to hold off on capital N and work out the two components of acceleration, the tangential and the normal components. So if I want to work out the parallel component right here, remember this is the component of acceleration who's parallel to velocity. So I could just work out a dot v over v dot v. And I'll find the part of acceleration who points in the same direction as velocity, the part who speeds you up and slows you down. So if I take my acceleration vector 2, 0, and I dot it with my velocity vector 3, 3, I'm going to get 6 plus 0 over the v dot v, that would be 9 plus 9, and I'll multiply that by my velocity vector 3, 3. So let's see, that's going to get me 6/18 times the vector 3, 3. Well, 6/18 is a third, and so that's just going to get me the vector 1, 1. Now that I've got the parallel component, I can find the orthogonal component by subtracting that off of the acceleration vector, just like we did a couple of units ago. So I will take the vector 2, 0, and I will subtract the vector 1, 1 from it. So that's going to leave me with the vector 1, minus 1. This is the orthogonal component. Now, I could double check my work really quickly by making sure that these two vectors, the parallel and the orthogonal bits, dot to 0. And if I dot them, 1 times 1 is 1, 1 times minus 1 is minus 1, and I get 0. These are, in fact, at right angles to each other. So now, how did all of that help me get capital N, the unit normal? Well, remember that the unit normal points in the exact same direction as the normal component of acceleration, but it's length 1. So I could get a hold of the unit normal by taking the acceleration's normal component and dividing by its length. We'll normalize that vector instead of t's derivative. So if I were to go and take the vector 1 minus 1, its magnitude would be the square root of 1 squared plus 1 squared. That will get me 1 over square root 2 times the vector 1 minus 1. And that's, I don't know why I put a comma there. That's equal to the vector 1 over root 2, comma negative 1 over root 2. And so now we've worked out all of the individual pieces. We have the velocity vector 3, 3. We have the unit tangent vector 1 over root 2, 1 over root 2. We have the acceleration vector 2, 0. We have the component of acceleration in the tangential direction, 1, 1. We have the component of acceleration normal to the velocity. And finally, we have the unit normal vector. One of the most common applications of vector-valued functions is in physics, in describing the motions of a particle. So imagine that you have some object in motion through the air. And it doesn't have any propulsion, so the only force acting on it while it's in the air is gravity pulling it down. This is sometimes known as a ballistics hypothesis. The only thing acting on this particle is gravity right now. Of course, like any good physics student, I'm assuming there's no wind resistance right now. If you want to figure out how to model this with wind resistance, take that in differential equations. So how would we describe the motion of this point right here? Well, Newton's second law says that the total forces acting on this object will equal its mass times its acceleration. Now, on the one hand, this is fairly easy for me to write in terms of calculus terms. If its mass is m, then its acceleration is nothing more than the second derivative of its position function. So there's mass times acceleration. On the other hand, in this case, there's only one force acting on this. So that one force is gravity pulling down. Now, physics says that the magnitude of this force will equal the mass of the object times a number called g, which represents the acceleration due to gravity. So this number g right here is equal to 32 feet per second in English units, or it's equal to 9.8 meters per second in standard units. And so this right here is going to be a vector who has no horizontal component and it has a negative mg. Points straight down with magnitude mg. Now, if I were to pull the m out of the equation on the right, I could sort of scale it out. I would have m times the vector 0 minus g. And if I divide both sides by m, I get p double prime of t is equal to 0, comma, negative g. This is sometimes known as the ballistics equation because it describes the motion of a particle traveling through the air after some initial firing. It also describes the motion of a particle falling straight down in free fall. It had no initial speed right here. Let's take a look at a sort of common example of this. A projectile is fired from the top of a 50-foot hill with an initial speed of 100 feet per second and an angle of elevation of 60 degrees. How high will the projectile go, and how far will it travel before it comes back to Earth? So here's a picture of the setting right here. And so I've got this projectile who's going to get fired out of this cannon, and so it will travel up, and then it will come back down to Earth right here. And it will smack over to there. I guess I got a little bit more grass in the picture. So the problem is asking two things. How high will it get? What will be its maximum altitude? And how far will it travel horizontally before it strikes the ground? So this is part A, and this is part B. How could we attack something like this? Well, the minute it's fired into the air, the only force acting on this projectile will be velocity, and so we can use the ballistic equation. And so we'll start with this equation here. P double prime of t is equal to 0 minus 32, since I'm using English units. Well, if that's the acceleration, then we could integrate both sides in order to get a hold of the velocity. So the p prime of t is equal to, well, we integrate each piece separately. If we integrate 0, we're going to get 0 plus a constant. If we integrate negative 32, we'll get negative 32t plus some other constant. Now, I need to work out these two integration constants, and that means I'm going to need to know some fact about p prime. So I'm going to need to know some initial fact about p prime. Now, what do we know about p prime of 0? On the one hand, if we plugged in 0, we're just going to get cd as my initial starting point. But I also know that it had an initial speed of 100 feet per second and an angle of elevation of 60 degrees. So I know that p of 0 is supposed to be a vector who looks like this. It has a magnitude of 100 and an angle above the x-axis of 60 degrees. Well, a vector like that, therefore, has components of 100 times the cosine of 60 degrees and 100 times the sine of 60 degrees. The cosine of 60 degrees is just a half, and so this is going to get me 50, whereas the sine of 60 degrees is root 3 over 2, and so this will get me 50 root 3. And so I now know the values of c, 50, and the value of d, 50 root 3. So let's make those substitutions right now. Now that we have the velocity, we could integrate this one more time in order to get a hold of the position function. So p of t is going to be the vector valued function who is the integral of 50 dt, comma the integral of minus 32t plus 50 root 3 dt. So if we integrate these two functions, we're going to get 50t plus some other constant, and then we're going to have, let's see, minus 32 times t squared over 2 would be 16t squared, plus 50 root 3 times t plus some other integration constant, f. Now how will we find the e and the f? Well, we could look at the initial position. If we plugged in time equals 0 into our formula, we're just going to get e and f. On the other hand, the initial position, well, it said that it was fired from 50 feet straight up, or 50 feet on the top of a hill, sorry. And so that means its initial position should be the vector 0, 50. And so we now know e and f. E is 0, f is 50. So we can make these final substitutions. And so let's collect the formulas we've just found. Position, velocity, and acceleration. Now we can answer the following two questions. How high will it go? So for the first part, remember we were firing upwards, and we were trying to figure out when it would hit this high point. Well, when it hits this highest point, that means it's going to be moving purely horizontally, because it should have a horizontal tangent there. So its velocity should have no vertical component. So we could solve for v of t equals 50, 0. Notice that the x-coordinate doesn't change at all. And we could find the time at which this occurs. So if we set this up, let's see, we're going to have negative 32t plus 50 root 3 is equal to 0. That means that 50 root 3 is equal to 32t. If we solve this for t, we're going to get 50 root 3 over 32. That can be reduced to 25 root 3 over 16, or approximately 2.7 seconds. So it takes 2.7 seconds to get to its highest point. Now what is that highest point? Well, that's what the position vector would tell us. If we take the position vector at 25 root 3 over 16, or 2.7 seconds, then we'll figure out how high it is by taking the y component. So now let's go and do that. I'll take the position vector, and I'll plug in 2.7. I'm not getting the exact value this time. I'm just shooting for a numeric approximation. It's got an x-coordinate, which I don't care about. And so all I care about is the y-coordinate, minus 16 times 2.7 squared, plus 50 root 3 times 2.7, plus 50. And if I work that out, I'm going to get 167.2. So how high will it go? About 167 feet. So we've got the first part taken care of. What about the second bit? How far will it travel? So really what we're asking here is we know it's going to go up and then it's going to crash back down to Earth. So if we can figure out when it crashes to Earth, we'll do the same trick. Now when it's back down on planet Earth, its position vector will be purely horizontal. So we could figure out when the position vector will look like some unknown value, 0. So that means we have to set the y-coordinate equal to 0 and solve for that. So if I take negative 16t squared plus 50 root 3t plus 50 and set that equal to 0, well, that's something that the quadratic formula could be used to solve. We would get t is equal to nasty mess that simplifies to about negative a half and 5.9 seconds. Now, the negative a half happens before the launch, so 5.9 seconds is the one we want. So 5.9 seconds is how long it takes to crash into the ground. Now let's take this time and plug it back into the original position function right here to figure out what our final position is. So we're going to have p of 5.9 is equal to the vector, well, its second component's got to be 0. That's how we found it. Its first component is going to be 50 times 5.9, and so that simplifies to 295, 0. So that means we traveled 295 feet before coming to rest. Now, in the last lecture, we talked about the integral of a vector-valued function. And I'd said that there really wasn't any sort of geometric meaning I could give you for this. If you happen to have a curve floating around in three-dimensional space, say this curve right here, and you gave me time equals a, so that would be, there's this point right here, there's the vector at time equals a, and then you gave me time equals b, then this integral, the integral from time a to time b of f of t dt, it wasn't the area underneath the curve, because the area underneath the curve would be a number, and this integral is always a vector. In fact, I couldn't give you any reason or any geometric intuition for this at all. However, I add one detail. I put a prime in here, and all of a sudden I can make this make sense, because the integral from a to b of f prime of t dt, we could use the fundamental theorem of calculus. We would find an antiderivative of f prime, and then evaluate that from a to b. We integrate the derivative, we get back the function, evaluate it from a to b, and so that becomes f of b minus f of a. I mean, that just looks like the regular fundamental theorem of calculus, but it has a meaning. If you have a vector and you subtract one vector from another vector, then that's the vector whose tip points at f of b and whose tail points at f of a. In other words, this vector right here, what's sometimes called the displacement vector from a to b, is exactly what this measures. So it's kind of bizarre. The integral of f doesn't correspond to anything at all on this curve, but the integral of f prime from a to b is the vector who connects f of a to f of b. What's even cooler, if I were to put absolute values on it, vector modulus, it turns out that this has a meaning too. We know that the magnitude of the derivative is equal to the speed. So what happens if you integrate the speed from a to b? Well, when we were in Calc 1, if you integrate speed, that tells you the total distance that you've traveled. Not just the displacement, but the actual total distance you've walked forwards and backwards. Well, if the integral of speed in one variable is the distance you travel in a straight line, then it makes sense that the integral of speed in three variables would give you the distance you traveled along this curve. And so that's what this integral right here measures. It measures what's called the arc length, how long you've traveled. So let me put all of these different vector ideas together in one common picture so we can see how everything interacts. You have some curve. You have a point in question, and this point is represented by a position vector, p of t, say. And this vector is footed at the origin. At this point, you'll have a velocity. So the velocity vector is the derivative. You also have an acceleration vector, which is the second derivative. There is a unit tangent, who we called t, and that was nothing more than the velocity vector normalized. We also have a unit normal n, and between the unit normal vector and the unit tangent vector, we can find the parallel and orthogonal components of acceleration. And now we've just seen this, that if we want to connect from this point here to this point here, where this point here corresponds to, say, time equals t1, then this green vector, which is a displacement vector, and this displacement vector is going to equal the integral from the starting time to the ending time of the velocity, dt. And last but not least, we have this actual length from here to here, the actual physical length we've traveled. This is called the arc length, and it's equal to the integral from the starting time to the ending time of the speed. And so these are the components of motion in three-dimensional space. That's pretty impressive. Let's determine the arc length of 4 full coils of the helix given by h of t equals the vector cosine t, sine t, t. Now you might remember we plotted this 2 lectures ago. This is sort of the standard helix that coils up the z-axis. So it starts at the point 1, 0 on the x-axis, and then it spirals around like this, going up the z-axis, and I guess also going down the z-axis if we follow it down this way. So what we want to do is we want to come up with the arc length for 4 full coils of it. So if I started here and followed it around, like so, well, this would be 1 full coil, and then 2 full coils, and then 3 full coils, and then 4 full coils. And so that's the length we're looking for. So the formula for arc length is that we're going to integrate from the starting time, t0, to the ending time of the speed, dt. So let's work out these important components right here. To get started, remember that speed is nothing more than the magnitude of velocity. So it's going to be the magnitude of the vector we get by differentiating h. So negative sine of t, cosine of t, 1. So the magnitude of this vector is going to be the square root of sine of t quantity squared plus cosine of t quantity squared plus 1 squared. Well, since sine squared plus cosine squared is 1, this gets me the square root of 2. So apparently, this standard helix moves with a constant speed. So I've got this part taken care of. We're going to integrate the function square root 2 dt. Now I just need to worry about the times. Well, it says 4 full coils. We could assume that the starting time is 0. That's when I'm at this point right here. And then we could figure out how long it takes to go and make 4 full coils. So how long does it take to make 1 coil? Well, it's kind of hard to see it in this picture, but imagine you were to look straight down the z-axis. In other words, we're going to look at the xy projection. When time is equal to 0, we're going to have cosine 0, sine 0 as my point. That's the point 1, 0. And then we know that in the xy plane, the equations x equals cosine of t, y equals sine of t, those trace out a circle going counterclockwise. And so when time is equal to pi over 2, we're at this point. At time equals pi, we're at this point. At time equals 3 pi over 2, we're at this point. And then at time equals 2 pi, we're at this point again. So it takes 2 pi units of time to make 1 full cycle. And so I guess that means it's going to take 8 pi units of time to make 4 full coils. And so this is the integral we need to work out. So we need to integrate the square root of 2 dt, and then evaluate that from 0 to 8 pi. Well, since this is a constant, we're just going to get the square root of 2 times t evaluated from 0 to 8 pi. So that gets me the square root of 2 times 8 pi minus the square root of 2 times 0, for a grand total of 8 root 2 pi. So that's how long this 4 coils of this helix is.